Okay, so in this video, I'm going to be going over the 2024 history past paper 1 of the externals and from QCAA. Okay, so let's just get straight into it. Okay, so I'm going to be a bit, I guess, brief in my explanations, just in terms of like time, because I have specialist paper 2 tomorrow, so that's one of the reasons. Okay, so question 1. Okay, it refers to hydrated copper sulfate. So we have this notation, and then we have a chemical reaction equation. The heat plus hydrated copper sulfate, and then a reversible arrow makes dehydrated copper sulfate, which is, solid, plus water as a gas, so water vapor. Okay, which of the following is exchanged with the surrounding environment? Hydrated copper sulfate is heated in a closed system to establish dynamic equilibrium. So what is a closed system? Okay, so regardless of the given information above, we could solve this question without that information. Closed systems are like a water bottle right here. So the lid is closed, the water doesn't go out, right? You can't exchange matter, but you can still exchange heat. So it's going to be A, right? You can exchange heat. If you can't exchange matter, it can't be B, C, or D because they all involve particles. If it was an open system, we were to open the lid. Now we can exchange both heat and matter. So it would be A. Question 2, same thing. Determine the oxidation number of sulfur. Same context, but now we're doing a calculation. In this, I'm not sure what specifically we need to demonstrate, so we know I'll just write copper sulfate H2O. Oxidation number, okay, so we know that the oxidation number for copper in this case is +2 because it's bonded, has an ionic bond with sulfate ions, and sulfate ions are negatively charged, right? It has a -2 charge, and since the compound is neutral, that indicates that, yeah, copper is +2. So if we were to solve this in terms of oxidation number, I actually don't know if we include the water, but in this case, it doesn't really matter because the answer should still be the same. Like, for example, regardless of whether we include water in this, let's actually calculate the oxidation number of this. It's 0. It's neutral, right? So 2 hydrogens is 2 times 1 because hydrogen is +1. It has an oxidation number of +1. Only in like, I actually don't know what the exception is for hydrogen. Okay, but oxygen, it's when it's hydrogen peroxide, I'm pretty sure. So H2O2, then it becomes -1. But in any other case, basically, it's -2. So -2 plus 2 is 0. Okay, but we know copper sulfate is 0 in this case, so this all goes to 0. Like we said, copper is +2. I'm trying to find sulfate. 4 and then times -2 because oxygen is -2. This is 0. This is not oxygen, by the way. Okay, so then it goes S plus negative, well, S minus 6 because it's -8 here. -8 plus 2 is -6. We add 6 on both sides. So S equals +6, which is B. Which identify which of the following is an essential component of an electrolytic cell. Electrolytic cells, we have energy being flown through the cell using a power source, right? We use a power source like a battery, something, yeah. Voltmeter. Voltmeters aren't mandatory. Okay, they're there to measure the voltage. That's basically it. Right? You can still have an electrolytic cell without a voltmeter. Salt bridges. You don't need a salt bridge for an electrolytic cell. Galvanic cells, you do need a salt bridge to maintain the charge neutrality. Is that how you pronounce it? I don't know. So it's going to be C. Identify which polymer contains a carbonyl group. Okay, carbonyl groups. It needs oxygen, right? It's given, in the question that the bond is given, right, in brackets. So it needs a carbon double bonded to an oxygen. Polyesters do have that, right? Ester bonds, ester linkages have carbon double bonded to an oxygen, but then that same carbon is single bonded to another oxygen, right? So yeah, A would be correct. Let's just see the other three options. Polyethylene only involves carbons and hydrogens, so no. Polypropylene, same deal, just now the monomer just has one more carbon in the carbon chain. Polytetrafluoroethene, kind of the same deal. Ethene, two carbons but no oxygen inside. Fluoro is the prefix for fluorine, right? Fluorine is not oxygen. Tetra is just how many fluorines are in the monomer, which is 4 in this case, but it's A. Titration is a volumetric analysis method used to measure the pH of an analyte. You do measure the pH of an analyte. It's not the entire purpose, but yeah, that is something, like for example, titration curves, we're familiar with them. We measure the pH, half equivalence point is where pH equals pKa, right? At the equivalence point, the acid completely neutralizes the base. That doesn't necessarily mean the pH is 7 at the equivalence point. So I'm inclined to think it's A. We'll check the other answers, I suppose, choices. Determine the volume of a titrant. You'd use a measuring cylinder for that. Typically, you're trying to find the concentration. Calculate the concentration of an identified solution. This is more in line with the actual use for titration. It's not just measuring the pH. You can measure the pH multiple different ways. Measuring the pH in this case is just a byproduct, I suppose, a side effect of the true purpose of titration curves. It's to actually determine what the concentration of the solution actually is, right? Of an identified solution. In this case, I'm assuming identified means like you know what the solution is, you just don't know the concentration. So it would probably be C. D, prepare standard solution of known concentration and volume. You're not preparing anything. You're not using titration to prepare solutions. Let's see. Identified solution, I'm assuming it means identified as in, like, for example, if you have sodium hydroxide, but you don't know its concentration. You've identified the solution, you just don't know the concentration, and you're calculating it using titration. Yep. The equivalence point of an acid-base titration occurs. We actually answered this inadvertently during our discussion in the previous question. Okay, it's the equivalence point is when the moles of the acid equals the moles of the base, or the concentration of the acid equals the concentration of the base. Those things are equivalent because we know that concentration is C equals N over V, right? When you're doing titration, they're in the same flask. So the solution that has both acid and base has a fixed volume. The volume is common. in both for both the acid and the base. Therefore, the concentration is going to be the same. You know? If moles are the same, concentration is also the same in this case for titration. By concentration, I mean the concentration of what's in the titration, not the sample used, right? There's a slight distinction that you need to be concerned about. Okay. So it's not when pH equals pKa. That's half equivalence. pH stops changing. That would be the final point. It's not endpoint. Final pH. Like, yeah, something like that. Indicator changes color. No, that's endpoint. Pretty sure. Titrant completely neutralizes the analyte. Yeah, that's basically the same thing I said. So it's D. Yeah. Which option is the principle of green chemistry? Okay, immediately, even without knowing what green chemistry is, you could insinuate, you could infer what it means, right? Like, let's say you get a mind like green. Okay, not greenhouse gases in this case. It's kind of the antonym of what we want. Green, we usually associate green with recycling, biology, right? Plants, vegetation, the natural environment. So green chemistry obviously links back to being environmentally friendly. So A seems in line with what green chemistry is for, you know, avoid chemical derivatives. We want to avoid byproducts, right? Decrease energy efficiency? No, we want to maximize it. We want to increase it. So it's definitely not B. Prevent catalytic reactions. Prevent catalytic reaction. I think catalytic means the use of a catalyst. We want to maximize catalytic reactions. We want to use them as much as we can because, you know, catalysts help decrease the activation energy. And obviously, that's actually very beneficial in terms of being energy efficient, which links back to D. Right? D, minimize atom economy. We want to maximize it. We want the reactants, we want as many reactant molecules that we use in the reaction to become the design product. We want to maximize it. If it's low atom economy, that means we use this much reactants, but then only this much gets turned into what product we want, and then we have this much byproduct. Not what we want. We want the opposite. So it's A. I might be going too slow right now, but I'm trying to break it down, you know. Determine the U-pact naming. The U-pact name of the organic compound shown. Okay, so we have 4 carbons. Okay, well, we can't eliminate any options based on the 4 carbons. 4 carbons, we go meth, eth, pro, bute. So bute is the prefix for 4 carbons. All of them have bute. We can't eliminate any options in this case. We should immediately be thinking butanoic acid for this. Like, we should get to that level, you know, especially now since chemistry is less than a week away. Okay. At the end of the carbon chain, what do we see? Oh, look at that. C double bonded O, and then there's also a hydroxyl group coming out. And so this entire group, this entire functional group, is a carboxyl group, and it's, you know, related to the carboxylic acid. Guess what? Oh, something ic acid. Oh, okay, it's A. If it was butanone, so the one or one, I don't know, but I'm pretty sure you pronounce it one. Ketone, right? It's the suffix for ketone. Ketone, it would be not at the end of the carbon chain, but it will it would have a carbonyl group. So C double bonded to O, but just in the middle of the carbon chain. Butanol would just be the hydroxyl group, so OH at the end, without the double bond. Butanol, aldehyde, it would be similar to what we see here, but instead of a hydroxyl group, all we have is a carbonyl group and then just one hydrogen attached to the carbon to satisfy the four different bonds that it can form. The carbons can form four bonds. That's A. Polytetrafluoroethene has a higher melting point than polypropene due to CF bond being non-reactive. Non-reactivity doesn't seem to have, well, it wouldn't really have any kind of relevance for the melting point. Fluorine atoms forming stable carbon to fluorine covalent bonds. Again, not really. Doesn't, because we know that melting and boiling point, they're dependent on the intermolecular forces. Inter meaning between molecules themselves. Intramolecular bonding would be covalent bonds, right? So, difference. There's a difference there. In this case, we're after intermolecular forces. They're not the covalent bonds, we're after dispersion, dipole-dipole, hydrogen bonding, right? So it's not A or B. Dispersion forces, dipole-dipole. Ooh, look at that. Okay, C and D look promising. Dispersion forces between closely packed fluorocarbon chains. Sounds pretty correct. Right, but let's continue. Dipole-dipole interaction between fluorine and carbon atoms. Would that be correct? I'm pretty sure, let me just double check. Let's see, on the formula sheet, we navigate over here, electronegativity. So carbons have a 2.6 value, and then fluorine has 4.0, so yeah, there would be dipole-dipole. However, pretty sure it's C. Here's my explanation. Let's just check. It is C. Okay. The reason being, I'll actually draw a graph here. The reason being, polytetrafluoroethane is a polymer. I'll draw the polymer. So, actually, no, the monomer first. So this is tetrafluoroethane, right? Ethane, because it's two carbons, and then there's double bond. So it's an alkene, right? But then there's tetra, so there's 4 fluorine atoms attached to those carbons. So that's the monomer. Not sure if you can see it very clearly, but I wrote monomer. To make this into a polymer, we use addition polymerization. So addition polymerization involves no byproducts. So what we do, we break the double bond, and then we just add monomers together. So then the polymer notation would be a single bond. And what we can do is we can just draw fluorine atoms going like that. Bonds going outwards. Make sure the bond extends beyond the bracket, because otherwise it's not correct. It needs to show that continuation in monomers, right? Attached to the polymer chain. We're also missing something, a lowercase n, to represent that, there's actually multiple monomers. If, for example, you were given like this three different monomers, you'd probably write 3. Okay, here it is. Remember, this was 2.6. 2.6. In terms of electronegativity, this was 4.0. So this is more electronegative than carbon. Right, so there's going to be a negative dipole produced here. Yeah. So this part is more negative. So there's a higher concentration of electrons here. But the same thing on this side, it's actually symmetrical. The same thing is happening. So it's like they actually counter each other. So then there's basically no net change. So then this actually wouldn't produce dipole-dipole forces. There's a slight trick here. But because, it's non-polar, then overall, right, then there's only dispersion forces being experienced as the primary intermolecular force. That's the explanation. At least it's my attempt at an explanation. Not sure if it's the valid explanation. Acid dissociation constant, it's on the formula sheet, represents the pH, no, of an acid solution. The strength, yes, of an acid solution, yeah. Concentration, no, you use the concentrations to calculate Ka. Conjugate acid-base pairs of an acid solution, no, it's B. Bronston-Lowry acid, it donates a proton to form its conjugate base. Okay. Conjugate is important, I think, in this term. Well, obviously, B is the same as D, except it doesn't have the word conjugate. So when an acid loses a hydrogen or a proton, it becomes a conjugate base, which then can accept a proton to become the original acid. So it's, for example, C would be, accepting a proton would be a Bronsted-Lowry base. Right. For example, water, it can act as, it's amphiprotic, so it can act as a Bronsted-Lowry acid or base. Yeah, it can donate a hydrogen or it can donate hydroxide. And obviously the conjugates, they can accept and donate protons respectively. Okay, so we have a equilibrium law expression. So it's the concentration of products over the concentration of reactants, and the powers represent the coefficients. This is on the formula sheet, I'm pretty sure. It's in terms of like A, capital A, B, capital B, C, and D, So the products are on the top. Okay. B and C, immediately, without even looking at the Kc expression, we can eliminate those immediately. Concentration, liquids do not have a concentration. So it can't be them. If it's aqueous or if it's a gas, then yeah. Also, yeah, that's about it actually. CO2, technically, even without looking at the states of matter, you can solve it. So it's A. Yeah. Since carbon dioxide is the only one at the top, that's a gas. Yeah. Okay, questions 13 to 14 refer to the reactions below. Okay, so we used dichromate as a catalyst for this reaction. We've noticed that reaction 1, the reactant, well, it's an alcohol. It's a primary alcohol. Primary alcohols can oxidize into aldehydes and then carboxylic acids. So this is an oxidation reaction. That's for reaction 1. Reaction 2, we have compound X, and then we have an amine. We use titanium chloride. Ooh, I might have to revise this. Yikes. But based on what we know, this is probably a condensation reaction between a carboxylic acid and an amine to form an amide. I just didn't know that you can use this as a catalyst for that. Okay, so type of reaction that produced compound X, immediately we've already recognized it was oxidation, so it was B. What is compound Y? Okay. It's not a substitution reaction, I can assure you that. So it's definitely not a nitrile. It's definitely not A. This is nitrile. C triple bonded to N. This here, for B, that's representing an amide, so it could be B. Like what we said, this compound Y that's produced is an amide. That's what we're thinking, but yeah. C is an amine. No, we're not just extending the carbon length, carbon chain. Probably not C. D, I don't know what's happening there. Yeah, that's very peculiar. Not sure what's happening there, yeah. So there's a carboxyl group, there's also an amine group, or amino group, since it's demoted. So it's B. Single displacement. Okay, so we're going to have a molecule with an anion, cation, and then there's one other molecule that's just by itself. It's probably metal. And then they switch. Simple. Okay, A, no, that's just, you're just adding copper with oxygen. Yeah, not single displacement. B, you're just separating the things, you know, they're dissociating. That's not single displacement. D, isn't single displacement, it's double displacement. C, yeah, that's basically, yeah. So nitrate switched and bonded with copper. This can only happen if the one that's switching with, so in this case copper, is more reactive than, in this case, silver, which I'm pretty sure is correct. All right, we can check our reactivity series table just to verify this information. Should be. Reactivity series of metals, we should notice that copper is above silver. Yep, copper's down here, so copper's not that reactive either, but it's above silver, which is Ag. So that's what permits this single displacement reaction. If those conditions are not met, obviously no reaction takes place. The simplified mass spectrum for an organic compound, carbon, there's 5 carbons, there's an unknown amount X hydrogens, and 1 oxygen. Okay, the parent carbon, the parent ion has a mole mass of 86. Okay. So none of these we can eliminate just based on, how many carbons we have and how many oxygens. They all have one oxygen and 5 carbons. So we can't eliminate it based on that. One thing we can recognize is 86. So the mole mass of these compounds should be 86. Okay, 71, the difference between 86 and 71, which is here, that's 15. So that means it's going to be CH3 at the end. Okay. Doesn't help much actually, but it's better than nothing. Um, you also have 43. Okay. So let's do some calculations here. Obviously, there's probably quicker ways you've been taught, or, maybe you're in the same boat as me, to be honest. I don't know. First, let's just draw 5 carbons quickly. Just 5 carbons. Okay, this is a non-negotiable. We know this is the amount of carbons we have, and there's one oxygen somewhere, right? Oxygen has a mole mass of 16. We know each carbon has a mole mass of 12. 12 times 5 is 60. And then we add these together, we get 76. What's the difference between that and 86? That's 10. So that means we have 10 hydrogens because one hydrogen is approximately one, mole mass unit, like atomic mass unit. Right, so there's 10 hydrogens. That's something to consider because if we have pentanol, which is the alcohol, we would have too many hydrogens. We would have 12 because we'd have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then OH, right? Or somewhere OH. Right, but in this case, it's pentan 1-ol. So it's going to be on the first carbon, whether it's here or here. That's 12. That's 2 more than 10. It's not going to be that. Okay. What about pentanal? In this case, we would have double bonded oxygen and then a hydrogen. So in this case, yeah, that is 10 hydrogens. But I'm pretty sure the same thing goes with the ketones, right? Just put hydrogens everywhere. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Same thing. If this moves here, it's also 10. Doesn't matter, right? Okay. We use the main peak in the thing. So 43 corresponds to exactly half of the molar mass of the entire molecule. So that's something important. Okay, let's consider this. We can just use guess and check in this case. Obviously, in an actual question, you should probably use a more standardized or methodical approach. Okay, so this we know we've already declared it's 15. Okay. 12 plus 3, which is 15. If I divide it here, how much is that? Okay. This is 15. What's this? 16 plus 12. That's 28. 15 plus 28 actually is 34. I mean 43. 43 is actually exactly what we want. We actually don't need to double check that the other side is 43 because we already know that we have the correct number of molecules, the carbons, hydrogens, and oxygens. So we can basically safely say that this is the correct one. Like, it's pretty safe to say that. Actually, no, there's a nuance here. I think I'm not too sure actually. Um, there's actually okay. Let's check the other spikes, right? So there's one around 58, 57. Okay. So if you go here, how much is that? So that's 43, right? And we add 14. That's 57. What about if we go the other way? How much is this? You know, this is 4 carbons, so it's 48. We have 7 hydrogens, so it's 55. Well, technically, we can do 86 minus 15, which is just 71. 71 does correspond to that. Oh, yeah, okay, no, that means it is correct, yeah. Okay. I was just trying to differentiate between pentanal, to be honest, and A. So it is A. That took a while. I think it's just because I'm trying to explain it. Identify the product produced at the cathode when a concentrated aqueous solution of NaCl undergoes electrolysis. Concentrated aqueous solution of NaCl undergoes electrolysis. Electrolysis means water can be involved in the reaction. We need to be aware of that. Let's look at our standard electrode potentials. Okay, too good at these, to be honest. I'm not like very quick at it. About how this works, to be honest. Um, well, immediately B's out of the equation. It's liquid, but it's a aqueous solution of sodium chloride, so it can't be B. Okay, produced at the cathode. Well, we use the remembering tool thing. It's a red cat, anox, red cat. We know that reduction happens at the cathode. Okay. It's going to be the forwards reaction. But in what way? Is it D? I don't know. I'm actually not too good with these. Like, is it the strongest oxidant that reacts with the strongest reductant? Or is it the one where the minimal amount of energy is used? Something like that, you know, is preferentially reduced or oxidized, something like that. I don't know, because my teacher said it's when minimal energy is used, right? Well, we're still revising, so don't be too afraid to make mistakes. I'm going with D. It is D. I'll just say I'm moderately confident because I don't know the proper explanation. I'm not extremely confident, or even though I got it right, you know. We know that water, as a liquid, can actually um, transform into hydrogen gas here and hydroxide ions. So hydrogen can be produced as a gas. So then would water also oxidize? to become this? See, that's the question. That's the question. Not too sure myself, which is not a good thing to be honest. Okay, the electrode and electrolyte solutions for four half cells are shown. Determine which two half cells will produce the largest potential difference. Well, platinum is inert, so the electrode is inert. So what we're going to have is iron, Fe plus 3, um, reducing into Fe plus 2. Okay. That the lowest? Yeah, I think that is. Voltaic cells or galvanic cells, that's an alternative name. So we're trying to find the spontaneous reaction that produces the largest EMF or voltage. Okay, so it seems like 4 is correct in terms of like it being the strongest oxidant. What's the strongest reductant in this case? Aluminum? Could be. Very well could be. I think it is. 3 and 4. It is D. Okay. I mean, for the galvanic cells, I'm pretty confident. Electrolytic, that's where things get a bit muddled. Esters undergo hydrolysis to form a carboxylic acid and an alcohol. So it's hydrolysis is just the reverse of esterification, and esterification involves a carboxylic acid and an alcohol to produce esters and water, because condensation reactions, you can kind of remember it that way, you know, condensation, water, condensing. Yeah. So it's C. And then finally, the polyprotic acid. Polyprotic means it can donate multiple hydrogens. You might think A, right? Oh, it must be A. No, it's a trick. Just because there's multiple hydrogens, well, there's multiple hydrogens for all four choices. E is a weak acid because not all hydrogens can dissociate. The hydrogens attached to the carbon have a non-polar covalent bond, so they don't dissociate in water. So only this one dissociates, so it's monoprotic. I can't really find an explanation for C. You're not donating hydrogen ions, you're donating ammonium ions, which I guess could be thought of as well, technically ammonium is a weak acid, is it not? Because isn't it the conjugate acid to ammonia, which is A, right? A is actually a base, so it's B. Okay, short response finally. Feels like an eternity, doesn't it? Okay. Because someone, right? Oh, someone, not naming names. Whoa. Renee is going very slow. Okay. Reactants A and B are placed in a 1 liter container, so volume is 1. Okay. And react to form product C. It's reversible, can reach dynamic equilibrium. Explain why a reversible arrow is used to symbolize this reaction. Okay, I'll give you the reason. The forwards reaction can occur, and the backwards reaction can occur to reach dynamic equilibrium. That's happening at the same time, right? And then dynamic equilibrium is just when the rate of the forwards reaction is equal to the rate of the backwards. You don't need to write all that. The reversible arrow indicates that the reaction occurs in both directions simultaneously. I basically said that. I'll accept a mark. Deduce whether the equilibrium for the reaction lies towards the reactants or products. Explain your reasoning. Okay, so 1 mark probably for stating correct direction, so whether it lies in the reactants or product. Explain using KC. That's probably 2nd mark. KC, it's greater than 1. We know that KC is the fraction, so it's the equilibrium expression or equilibrium constant. So the concentration of the products over the concentration of the reactants. In this case, it would be concentration of C over concentration of A times the concentration of B. Okay, if the concentration of C is greater than the product of the concentration of A and B, guess what? It's going to lie towards the products. That means it lies towards the products. If that's the case, it's going to be the fraction is going to be greater than 1. In this case, it's greater than 1, so it lies towards the products, since Kc is greater than 1. Kc is greater than 1, explains Kc is greater than 1, deduces it, that equilibrium lies towards the products. Okay, 4 marks, I'd say. Describe the type of reaction that occurs when amino acid monomers are joined to form polypeptides. This is difficult to be. Wow, that's pretty generous, to be honest. I mean, I guess, whatever. Type of reaction that occurs, amino acid monomers. It says describe, so it's not just like, oh, you say condensation, polymerization, and then you're done. No. It is correct. That's 1 mark, probably. Because amino acid monomers, when they combine, you use condensation polymerization. So they lose the hydrogen, lose a hydroxyl group, and what happens to the hydrogen and hydroxyl group? They bond together, they form water. Condensation. You know, we said this before. Come on. Okay. Form polypeptides. Okay. Amino acid monomers join together, forming peptide bonds. Oh wait, that's literally part B. I just realized that. They undergo condensation polymerization to join together and form water byproducts. Condensation reaction occurs when amino acid monomers are joined to form peptide bonds and water. What? Water is removed. Describes that water is removed when amino acids. Okay, so you don't need to say peptide bond. I know peptide bond is the answer for B, but yeah, I don't know why they wrote it for A. Yeah, okay. So 4 marks for that, I'd say. An aqueous solution of sodium hydroxide is titrated with a 30 milliliter aliquot of 0.012 capital M per moles per liter potassium hydrogen phthalate standard aqueous solution. Balanced chemical equation. The reaction is shown. It's not reversible, but it seems reversible. It seems like potassium hydrogen phthalate is a weak acid. The results are shown in the titration curve. Determine, oh my goodness, speak of the devil. Determine whether KHP is a strong or weak acid. Identify one feature from the titration curve to support your reasoning. Okay, what I meant by it doesn't look like a strong acid is because, oh look, we have a buffer region. Buffer region shows that it's resisting the change in pH. So initially, we can see the steepness of the graph. I'll zoom in. Maybe it's actually worse if we zoom in. Okay. Initially, right, at the y-axis, so at the pH axis, you can see that the rate of change is like steeper, and then it actually lessens a bit. I don't know if it's more noticeable here or something. Also, another feature you could use is at the equivalence point, guess what? pH is greater than 7. And since we're using a strong base, which is sodium hydroxide, that means we're dealing with a weak acid for KHP. So you can use buffer region or coolants. Oh, whoops. Okay. Titration curve. There's buffer region. Explain why KHP is used as a standard solution, as the standard solution rather than NaOH. Um, what? Why is this used? Okay, I'll be honest. I have no clue. What? Hmm. I'm actually curious. I can't explain it. It's one mark, which is surprising. It's explain question. KHP does not absorb water from the air. What? Okay, hopefully someone can explain that to me. I need help as well, you know? I need help, you know? This is a mutualistic relationship. Goes both ways, you know? Um, it it doesn't absorb water from the air. Are we meant to know that? What? Wait, I've never heard of this. Are we meant to know that? Like, in the syllabus? Whoops, okay. I almost saw the answers for the next part. Therefore, an accurate concentration. Like, okay, you know, the part after the semicolon makes complete sense. If it can't absorb water from the air, okay, you can get an accurate concentration. But how am I meant to know that KHP does not absorb water from the air? Does that mean sodium hydroxide absorbs water from the air? What? I'm a bit lost here. Calculate the concentration of NaOH. Okay, yeah. Well, guess what? We can use the equivalence point, which is where the moles of the acid equals the moles of the base. So the moles of sodium hydroxide equals the moles of KHP, right? Potassium hydrogen phthalate, at the equivalence point, which we achieved by using 25 milliliters of sodium hydroxide. Okay, so let's do this. Right, at equivalence, I'll just use the at symbol. You know, why not? The moles, so n, lowercase n, to represent the moles of NaOH equals the moles of KHP. Right? When you add the number of moles of sodium hydroxide. Wait, what was the question asking for? I forgot. Um, the moles equals the concentration times volume. The concentration. Oh wait, are we trying to find the concentration? Concentration of. Okay. Yeah, I was confused there. So actually using moles of this. So 0.012 times 0.03 because we're converting 30 milliliters into liters. Okay. And then N equals CV. How many moles did we how much volume did we use? We used 25 milliliters of sodium hydroxide. So we divide that by 0.025 liters. We basically divide the volume in milliliters by 1,000 to convert to liters. We should go a bit quicker. Answer this 0.0144. That should be our concentration. So in terms of scientific notation, 1.44. Okay. So we basically did that. Yep. So marks there. Oh, I didn't want mean to press 5, but okay. Because of part B, I didn't really understand that. The pKw of pure water at various temperatures was determined to investigate the effect of temperature on the equilibrium position of self-ionization of water. The results are shown. Explain the effect. How many marks? 4 marks. Explain the effect of increasing the temperature on the pH of water by considering the enthalpy of the Ford's reaction. Okay. As temperature increased, pKw decreased. Okay. That's pretty basic trend, to be honest. Identifying a very basic trend. If pKw decreased, that means kW increased. Given that we know that kW, or we don't necessarily need to know the exact stuff on the graph. We just need to know that pKw equals negative log the base 10 of kW. If we convert that and rearrange for kW, we get kW equals 10 to the negative pKw. So as pKw decreases, this actually increases kW. And we know that kW equals the concentration of hydrogen ions times the concentration of hydronium. Not hydronium, hydroxide ions. Hydronium is H3O+. So this increases. Therefore, obviously in the exam, you'd write this in words. I don't think you'd be, maybe you would, if they're being generous, but I think you're meant to write it in words, in sentences. As kW increases, right? So up arrow kW, you know. No, I meant to say as temperature increases, kW increases, which then means concentration of this hydrogen and hydroxide ions is also increasing. That's poorly written. So I'll rewrite it. There we go. If this is increasing, we know that self-ionization of water is like H2O liquid and then plus aqueous plus OH minus aqueous. So the hydronium and the hydrogen ion and hydroxide ion, they're both products in the self-ionization of water. So as temperature increases, the products are increasing as well in concentration. What does that mean? If it's increasing the products, well, if you're increasing the temperature, according to Letelier's principle, it's going to try and decrease the temperature. And if it favors the Ford's reaction to decrease the temperature, that means the Ford's reaction, therefore, is endothermic. So obviously, you'd write what I said, basically. So self-ionization of water is endothermic. That's the overall thing. As temperature, okay, what? This is literally basically what I did. It's very succinct, actually. It's just instead of using symbols, they use words. But overall, it's basically the same. As temperature increases, pKw decreases, and then in brackets, which is grayed out, kW increases, indicating the equilibrium shifts towards the product. Therefore, the Hall's reaction is endothermic and increasing in temperature increases concentration of hydrogen. Oh, it says pH. Okay, decreases pH. We're trying to go fast here, so fair enough. Decreases pH. I mean, yeah, I know that. I'm just trying to go fast here, to be honest, because pH is essentially the same thing as pKW. Right, pH equals negative log base 10 of the concentration of hydrogen ions. So as this increases, this decreases because there's negative out the front. Yeah, simple. Maltose is a disaccharide or disaccharide formed when two monomers of alpha glucose are joined. Identify whether alpha glucose is an aldose or ketose monosaccharide. Let's look at the formula sheet. Alpha glucose is an aldose, but let's just look at the formula sheet. So we can see that the forms for glucose and fructose are actually given. So if we're dealing with glucose in this question, let's look at glucose. Straight chain, okay. Aldose and ketose, those are just words for saccharides in terms of aldehyde, if it's an aldehyde or if it's a ketone. Like aldose, aldehyde. Ketose, ketone. In this case, glucose, you'll notice there's a CHO group at the end. If the carbonyl group's at the end, it's an aldehyde. So that's going to be an aldose. Okay. Distinguish between alpha glucose and beta glucose. So it is an aldose, not aldehyde, aldose molecule. Aldose monosaccharide. Okay. Alpha glucose and beta glucose. Well, alpha glucose, the hydroxyl groups at the first and fourth carbon, they oppose each other in terms of direction. They're going in opposite directions. Beta glucose, they go in the same direction. Yeah, something, to that effect. Okay, so you can use trans or cis as the terminology for whether the alpha glucose has it on opposite sides of the carbon ring. So this would be in terms of the geometric isomerism, by using those prefixes, right? Aldose, its opposite sides, yep. Should group on, yeah, beta glucose as the same side, yeah. Okay, so same thing. Aqueous potassium iodate reacts with aqueous potassium iodide in the presence of dilute HCl to form solid iodine. The overall balance equation is shown. Identify the reducing agent. I did not. Oh, okay. I forgot to switch the screen. I apologize. Identify the reducing agent. The reducing agent is the one that oxidizes. Not too good at these questions because I get a bit confused. In the mock exams, I got a bit confused. Yep, I'm a bit confused. Okay. The reducing agent would be the one that oxidizes. In this case, what oxidizes? Well, we would be dealing with oxidation numbers. So chlorine doesn't change, it's still -1, right? It's HCl and then it becomes KCl. It's bonded with a cation with +1 charge in both scenarios, so it doesn't change. We have potassium iodate, so iodate and iodide. I'm assuming that iodine is affected. Okay, so for potassium iodide, it actually oxidizes. because it goes from -1 oxidation state, oxidation number, to 0 in the product side. So it's increasing, which means it's oxidizing. Okay, so it would be I negative, right, given oxidation number increases from -1 to 0. Yeah. It loses an electron to be oxidized. Oh, okay. Loses an electron to be oxidized. I mean, same kind of thing, right? Oxidation number increases, loses an electron. Yeah. Determine the reduction half equation. Reduction would mean it's the one that reduces. Yeah, so, but it's not this. It would probably be the other iodine. Yeah, it probably is. Let's actually calculate the oxidation number. Okay, so with K, which is +1, because it's a group 1 metal. Oxygen, which is -2. So it's going to be -6 plus 1, which is -5. And then I is 5. And then in the product side, it becomes 0. So it reduced. Simple. Okay. Um, this is in acidic conditions. I believe it is. Is it? Yeah, it is, because there's acid involved. So we can use codes, right, to balance this, I think. I'm not good. I'm not good at this because this is something I got wrong in the multiple choice in the box. Yeah. Let's use black pen. It looks better. More, like here, blue pen is quite faint, so hopefully it should appear better. Okay, so we're dealing with iodate, which is IO3 minus, and then we have an arrow somewhere because we're going to have a lot of different reactants to balance this. And then overall, we have iodine, and then make sure states are correct. So it's solid and it's aqueous. And then I think all we do is just balance. So iodine, so COS, KOH, ES, right? So the key elements, which is iodine in this case, so we balance them. So there's 2 iodines now in both sides. Oxygens, we need to balance the oxygens. How do we balance oxygens? We add water. 6 oxygens here, so we add 6 water molecules here. Hydrogens, next to hydrogens, we need to balance the hydrogens, so there's 12 hydrogens here, there's no hydrogens here, so we add 12 H plus protons here. Yeah? Okay. Electrons, so the charge, right? We use electrons to balance the charges. Here, over here, we have 12, right? So positive 12 plus 12, and then we minus 2. So it's positive 10 on this side, while we have 0 on this side. So then we have to put 10 electrons here to balance this charge. And then states should be okay. Hopefully this is correct. I don't know. I'm not certain. This is good. This is good. Okay. Good. Very good. Okay, determined IO3 minus plus H plus electrons are reactants. That's 1 mark. Determines iodine, it's a diatomic iodine, and then water are products, determines the balance reaction, which is 3 moles. Okay, so states aren't required, but I still got them. Okay, that's good. We actually got that. I'm actually pleased with that. That's actually very good. Very good news. A series of experiments was performed to investigate the optimal reaction conditions to produce biodiesel from seed oils using a two-step process. These are the bulky questions, the complex questions. Acid esterification using an acid catalyst. Transesterification using ethanol as a solvent and magnesium oxide as a nanocatalyst. What? Transesterification is something I forgot, but it's like when you have multiple esters, then you combine them to make a triglyceride. I think biodiesel, glycerol. Oh, don't think it's glycerol, but I think it is triglycerides to an extent. Yes, when you combine multiple esters. Okay. The experiments measured the effect of the catalyst with concentration in ethanol to seed oil ratio and temperature on biodiesel yield. Temperature was held constant when investigating the effect of catalyst concentration. Okay, temperature needs to stay constant, which is good. Okay, the results are shown. Identify the optimal reaction conditions to maximize biodiesel production. This is pretty easy. 1 mark. Ah, wow. Okay. I mean, fair enough. It's very easy. You just look at the graph. Okay, what's the maximum yield? Okay, it's at 4% for catalyst concentration. Ethanol, it's at 10 grams per gram. Yep, and then temperature, it's at 45 degrees. So it's 4, 10, 45. 4, 10 to 1, which is basically what I said. Yeah, grams per gram. And then 45, yeah. Explain why both esterification and transesterification reactions are used to optimize biodiesel production. Okay, there's a reason why I'm taking a drink of water is because I have no clue. I have no clue. Optimize. Let's guess. Optimize biodiesel production. What I remember is there's lipase, catalyzed transesterification, and base catalyzed transesterification. Okay. Alright, well, first, let's think about it. Okay, we use. What do we use to turn. What do we use? What's the reactants in the acid esterification? Um, it's not just normal carboxylic acids. In terms of this, right, biodiesel, we're going to be using lipids, you know, fatty acids. So we're going to be using, you know, fatty acid molecules, or free fatty acids in this case. And then they're going to undergo esterification to form fatty acid methyl esters because they become esters, like FAMEs. I remember that acronym. Yeah, fatty acid methyl esters. And then transesterification, you use those FAMEs, right? FAMEs, to produce triglycerides, or in this case, biodiesel. So it's not triglyceride. And that produces the most efficient. That's the most efficient method. I don't know. Mate, I don't. Some effect that counts. Okay, that should be easy. That's that, at least. Why is it a common theme in this paper where part B is something just mind-boggling? It's always part B, and it's always explained. The one before, remember, a while back, like question 22, 23, I don't know. It was explained, but it was 1 mark, and it was like, oh, potassium, hydrogen, phthalate, sometimes all water. Like what? What? I mean, this one, it's something I should know, so I don't really have much of an excuse. In esterification, free fat. Hmm? Acids react. Okay, no. I thought I was close. I wasn't that close. Free fatty acids react with an alcohol to produce esters in water. Okay. Fatty acids react with an alcohol to produce esters in water. Yeah, okay, I understand that. In transesterification, esters react with an alcohol to produce fatty acid alkyl esters, biodiesel, and glycerol. Yeah, and glycerol, I know that. Um, a two-step process maximizes the conversion of FFAs to biodiesel. Is it because if you have multiple different processes, like let's say you have 3 or 4, 5, 6, 7, 8, since you can't have a 100% experimental, um, you can't have 100% energy efficiency in these processes. So therefore, with each added conversion process, you're going to be losing energy somewhere. So in this case, it's very optimal if you just have 1 or 2 processes. That makes sense. That makes sense. I thought it was more kind of knowledge based, but alright, whatever. It's just because there's only 2 steps. And then we just explain what happens in esterification and transesterification. Esters react with an alcohol to produce fatty acid alcohol esters. Okay, I'm learning with you guys. Don't worry, we're in this together. Okay. Whoa. Okay. Determine the effect by catalyst. This is pretty easy. Okay, 4 marks. It's going to be 3 marks for correct effect, like trend. 1 mark for correct, like data to support for each. Simple, right? Like, okay, so it's just for all 4. Catalyst concentration improves. Higher catalyst concentration percentages improve biodiesel yield because they lower the rate of the activation energy. I don't think you meant to say all that, but I don't know. Okay, well, at 0%, it's 91% biodiesel yield, and at 4% catalyst, increasing it to 4% catalyst, increasing the catalyst concentration to 4% increases biodiesel yield to approximately 92.7%. Yeah. Okay. Conversely, increasing the ethanol to seed oil ratio, no, higher proportions of ethanol to seed oil um, diminish biodiesel yields as increasing the ethanol to seed oil ratio from 10 to 18 grams per gram decreases the biodiesel yield from 93.2 approximately percent to 91.4% approximately. Okay, and then increasing temperature has an adverse effect on biodiesel yield, as increasing temperature from 45 degrees to 70 degrees Celsius decreases the yield from 92.3% to 92 approximately. What? No, you don't even need to say anything like related to chemistry. You just go increasing it to this, led to an approximate increase, increasing it to this, decreased. Okay. I'll give myself 3 for that because part B. Yeah, that's kind of the only reason. We're actually going all right in terms of time, which is surprising. That's only because, yeah, I noticed this for physics as well. It's because I'm not actually writing my answers. It takes time to write the answers, right? But I'm just verbally answering the questions, and I'm not really saying the words I would write. I'm being very succinct, but saying the key points and stuff, but not in the correct structure. That's why for physics and this video, I can actually kind of go within the time limit. Okay, so 29 is the last question. So we have 2 more questions to go. It's actually pretty good. Explain why the isomer is a saturated compound. No double bonds, it contains the maximum number of hydrogens that it can take up. Okay, I'm not going to check the answer yet. This is 4 marks. Wow, very generous. Next question. What? No way. I mean, to be honest, to be fair, this paper, easy questions, and then difficult questions. Difficult in terms of theory, there weren't really any calculations for this paper, right? But just besides those 2 questions, every other question seemed pretty easy. Seemed pretty chill. Saturated compound, like I said, because it contains the maximum number of hydrogens the molecule can have, and no double or triple bonds, right? Yeah. Identify whether isomer is a primary or secondary haloalkane. Okay. Primary, secondary, tertiary. That's dependent on. Let's actually draw it. We haven't really used our book much today. Look at that. Look how much writing we've done. Hardly any. I mean, obviously we have the other page, but whatever. Okay, let's say we have chlorine, which is indeed what we have right now, and then we just have carbon attached to hydrogens. This is an example. Well, this isn't even a primary, actually. Is it? Is it? No, this is primary, I think. Yeah, this is primary. The carbon the chlorine's attached to, so this carbon is attached to another carbon. Only one carbon. Right, so the haloalkane, or the halogen, is attached to a carbon that's only bonded to one other carbon. So this would be primary. So we can write 1 degree, which is a notation for primary. Secondary, hopefully you can see the pattern, right? We have chlorine in the middle. It's attached to a carbon again. So this halogen is attached to a carbon, and this carbon is not just attached to one carbon, but it's also attached to 2 carbons. So it actually forms 2 bonds to 2 separate carbons. Or it forms a bond to 2 separate carbons. So this would be secondary because there's 2 carbons attached to the carbon that the halogen has. Tertiary, same deal. However, in this case, there's 3 carbons. Okay, I'm not going to draw the hydrogens just for simplicity's sake. So we have the halogen, in this case chlorine, once again. This is attached to one carbon, and this carbon that the halogen is attached to is also attached to 3 different carbons. This is tertiary. This principle applies to alcohols as well. So if you have a primary alcohol, same thing. Same kind of deal. Secondary alcohol, tertiary alcohol. So if you're differentiating between primary and secondary alcohols, you can get it from the position, or you can get it from the products from oxidation. So if you oxidize a primary alcohol, this is, by the way, these aren't alcohols, obviously, but let's say the chlorine was replaced with a hydroxide group, using, you could use substitution reactions, couldn't you? But if you have like sodium hydroxide with ethanol solvent, yeah, that is correct, right? Heat it up as well, then they can switch, I'm pretty sure. Yeah. The primary, you oxidize it, you get aldehydes and carboxylic acids. Secondary, you get ketones. Tertiary, you don't get a reaction. We went off a little tangent. So in this case, the chlorine is only attached to a carbon that has one carbon-to-carbon bond. So it's a primary. Tertiary compound, only single bonds. Okay, so I did say that. Primary haloalkane. Yeah. Okay, 2 marks for part C. Determine the structural formula of another isomer of C4H9Cl that is a tertiary haloalkane. So part C does link. Okay. C4H9Cl. Well, the thing is, it's very simple because this is literally it. Excellent. Time management. Look at that. We inadvertently did part C just through explanation. So this is the only possible tertiary thing because the isomer only contains 4 carbons, and in this case, to have a tertiary haloalkane, you need 4 carbons minimum, and it must be in this kind of arrangement with the chlorine attached to this central kind of carbon atom. And then you have 3 hydrogens branching off each of the individual carbons, except for the central carbon. And that's where the 9 hydrogens come from. Yeah. And then how would you name this? Okay, let's think about it. What's the longest carbon chain? It could be this, it could be this, it could be this. It doesn't matter because all in all 3 of those different variations, you get the same kind of the same amount of carbons in the main chain, which is 3. So meth, eth, prop, 3. So prefix is prop. We're dealing with an alkane because it's only single carbons. The propane. Is it just propane? No. No, it isn't. We have chlorine. Chlorine substituent, right? A halogen. So it's a haloalkane. But we also have a methyl substituent here. And these substituents are both at carbon 2. Something to note. Since this is a substituent, you'd think, oh, you have to write 2-methyl. But since it's propane, I'm pretty sure that would be incorrect because there's no other place, there's no other position that this substituent can be placed in terms of propane. Because if it was placed on this carbon, that would extend the main chain and it would no longer be a substituent, it would be part of the main chain, and then it wouldn't be propane, it would be butane. Same thing here, right? If you move it here, same thing happens. chlorine and methane, not methane, methyl. You have methyl, right? And you have chloro, which is the prefix for chlorine when it's a substituent, right? So this is a haloalkane. When you're ordering substituents, you need to order them in terms of alphabetical. So C comes before M, so it's actually 2-chloro. The reason why there's the locant 2 out the front of chloro is because chlorine can actually be here, right? And it wouldn't change it wouldn't change the length of the main chain. However, for methyl, it would. So methyl can only be there. 2-chloromethylpropane. I believe that's the correct answer. So let's see. Determine the structural formula. One. Okay. Seems like they actually put 2 out the front. I would actually disagree with that. I actually disagree with that. There are some cases where I've seen it for the Specialist 2021. I remember that was streamed. It was paper 2 2020 Specialist. I asked my teacher about it. He did agree with me and said that there are 2 possible answers, but QCAA didn't actually demonstrate that there's 2 possible answers. I disagree with this, and I'm pretty sure my teacher disagrees with this because my teacher specifically said that in these cases, when you're dealing with propane and you have methyl substituent, no locant. Adding a locant would be wrong because there's no other position. You know, the locant kind of implies that you're basically specifying the position. But in this case, there's no need to specify it, right? Either way, they basically mean the same thing. But yeah, I would accept my answer. I might be wrong, but I'm pretty sure I'm right. I'm pretty sure. Methylamine is a weak base that forms a buffer solution when mixed with methyl ammonium. Describe using a diagram the structural formula of methylamine. Okay, so just draw the structure. That's what it's saying. Methyl amine. Wow, look at that. 1 mark in less than like 10 seconds. Methyl substituent, amine. Easy peasy. Apply Le Chatelier's principle to explain how the methylamine methylammonium buffer solution would resist a change in pH with a small amount of NaOH it was added. So sodium hydroxide was added. I like these questions. I like these questions a lot because they're pretty simple. First, let's actually verify the structural formula. Yep, that seems to be coherent with my answer. Yep. Good. Okay. Part B. Let's talk about it. Okay. Well, first, what happens? If we add sodium hydroxide, we know it will dissociate into sodium ions that are positively charged and then the hydroxide ions that are negatively charged. We know that in the methylamine and methylammonium buffer solution, hydroxide ions are actually a product. So by adding a small amount of sodium hydroxide, you're actually increasing, since the hydroxide ions dissociate, you're effectively increasing the concentration of hydroxide ions within the buffer solution. If you increase the concentration of the hydroxide ions, according to Le Chatelier's principle, right? I don't know how to pronounce it. I don't know if it's like Le Chatelier's principle or Le Chatelier's principle. I don't know. I'm not French. But what I do know is what it's asking. Okay? If you increase the concentration according to the principle, it's going to try and decrease it. The system, is going to try and partially oppose the disturbance made to re-establish equilibrium. Therefore, by increasing it, it's going to try and decrease it. To decrease it, it's going to favor the reverse reaction. It's going to use up the surplus of hydroxide ions as and convert it into methylamine and water. Okay, and that would help ensure that the concentration of H plus ions does not decrease, right? Because we know that H plus can combine with OH minus to form water. Yeah. Allowing pH to remain basically the same. I think I explained that. Added OH minus will react and accept a proton to form water, and thus equilibrium would shift to the left and resist a change in pH. Yeah, I basically said that. Yeah, excess OH ions would react with them. I said like a surplus of hydroxide ions would then allow the formation of methylamine and oh, okay. Well, that's paper one done of chemistry for not the externals, just the past paper. Let's not get ahead of ourselves. Okay, because just doing the past papers doesn't mean anything. We need to understand it, and we need to replicate it, in the actual exam. So overall, I think that's it for me. I mean, definitely because I'm a specialist tomorrow. But yeah, hopefully that helps somewhat. Hopefully, I don't know. Yeah, I'll try and make a video tomorrow. But catch you later. Peace.